I'm going to be Mackenzie, and I'm going to be talking about a 3D rendering engine for Elm. I was actually just thinking today, that sounds like a really intimidating headline. It sounds like something you use like Pixar to make like the next like super animated movie. That is not what the idea is here. It's meant to be something a little more approachable than that. But let's see, let's take a look. So it's a little bit about me. I'm a software developer at Arup. It's a big sort of civil engineering consulting firm. And as you mentioned, I'm author of sort of a couple of different geometry-related packages within the Elm ecosystem. And I want to use Elm to design things like robots eventually. So this is actually a sort of a diagram of a part of a robot that I designed many years ago. You've got sort of a drive motor here, sort of your actual wheel there, which is making the robot move. You've got some sort of steering mechanism up here. You've got a motor in here driving a bunch of gears that eventually drives this wheel. So sort of relatively complex stuff to design. And what often happens is you want to make changes, right? You want to, little stuff like, oh, I want to make the wheel a little bit bigger. Fine, easy enough. Bigger stuff like, can you take that motor and replace it with this other motor? Way more annoying. And it's a different gear size. You have to go redesign a bunch of things, move a bunch of stuff around. It's really sort of annoying and tedious to go into your CAD program and change this and shift this around. But as programmers, we don't like repeating ourselves, right? We don't like doing the exact same process over and over again. We write some code that does that. And so what I sort of got to after a while doing this is that I decided I want to be able to write code that created these complex 3D shapes. And then anytime somebody wanted to change something, you just change one little bit of the code, run it again, get a new design out. I want to do Elm to do this because Elm is awesome. And so what do we need to be able to do something like this? I mean, first, you need to generate sort of 3D shapes, and that's a lot of what Elm geometry is all about. You also need to be able to display those 3D shapes so you can see you're doing this, and that's kind of what today is all about. So as a simple example, here's sort of a little example of a little microscopic part of a robot that one might design. This example I came up with a little while ago. And so here we've just got sort of a metal shaft and a couple of sort of ball bearings to let it spin. You've got a sprocket on here that might drive a chain somewhere. And here you can vary different parameters. So we can see what does it look like if we try out some sort of different shapes for that sprocket. And this is not that exciting. We're not changing anything too fundamental, but you can imagine sort of arbitrary, interesting logic going on here that redesigns this completely based on some cool logic that we'd write in Elm. So something like this, hands up, who would think they could just go home and just take a couple days and write this? That's basically what I thought. I expected. This is that's sort of the point. So that's what this talk is all about. Let's make some better ways to do those sorts of things in Elm. Just a final note, one more thing you might want to do here is actually take those things and export them into some format so you can actually go build it, whether that's 3D printing or CNC cutting. This is an area I'm super excited about, and so maybe another year or two I'll be talking about actually building things with Elm, but we're not quite there yet. But today, all about 3D rendering. So what does it look like? You can definitely do 3D rendering in Elm right now. That builds on top of WebGL, which is JavaScript's way of doing, taking advantage of your graphics card. So it exists as part of the standard web platform. It's very low level. It's extremely stateful. I mean, even by the standards of object-oriented programming languages, there's massive amounts of hidden global state you've got to track really carefully. Super painful to use. You can do some cool stuff, but it's not a lot of fun. So in Elm, we already have the Elm Explorations WebGL package, and that is basically a functional wrapper around the JavaScript API. So it's way easier to work with. As somebody who's worked with both, it's a ton of, I really enjoy it, but it's still quite low level. You end up having to you have to write things like shader programs. You have to learn this whole new language to sort of run your graphics. You have to worry about transformation matrices and a lot of funky math. So still not, I don't think, often what you'd want to do most of the time. So I started thinking about what would it look like to have a 3D rendering engine, sort of the design from the ground up for Elm. So what's Elm like as a language? I mean, it's very approachable, it's very friendly. So doing simple things should be simple. There shouldn't be a huge amount of overhead. We should have sort of nice high-level functionality. For 3D graphics, we should have the pretty high-level functionality for doing things like throw in a light, add some shadows, create some shapes, have a particular material on those shapes, these sorts of things, without having to worry about a whole bunch of crazy low-level math. It's also strongly typed, right? So things like the position of a light or an object and the direction of something or the color of something, you can all represent those as 3 floating point numbers, X, Y, Z, RGB, and often this is what people do in lots of different packages. But really, those are 3 completely different things, right? We should use different types to distinguish between those and make sure you don't mix them up. Another big one for me, as you may have guessed, as author of the Elm-Units package, I'm a big fan of using proper units for everything. So we've all sort of decided that if we want to render a cube, we say it has the size of 3, and this is fine. And like, 3 what? Like, no, I mean, a cube, it gets 3 meters wide, or 3 feet wide. And I really like using, having proper units and physical units for everything, because I think it lets us use our intuition from the real world, where we live in 3D all the time, and apply it in our code. So, sort of thinking about a lot of these different things, decided, okay, let's take a crack in this, and let's try to come up with a 3D rendering engine, 3D graphics framework for Elm. So, what that led to was Elm 3D Scene. So it's again, high-level 3D graphics framework. It's designed from the ground up for Elm. So it takes inspiration from other packages. If you've done sort of 3D in JavaScript before, 3.js is an obvious example, but also like gaming engines from like desktop games. So Unreal, Frostbite, they have a ton of great documentation out there that I took a look at, sort of drew inspiration from. So it takes inspiration from all these, but it's definitely not a port. This is not like a port of 3.js to Elm. This is its own thing for Elm specifically. And by the way, pretty much all the images in here at this point were generated using Elm 3D Scene. So here's one example. Sort of alluded to this before, but it supports both sort of very complex and very simple scenes. So personally, I'm really excited about doing things like robots and spaceships and buildings and designing for really big complex stuff with physical materials, metals and plastics and rubbers. So that's sort of what I'm excited about personally. But lots of people want to make awesome, cool games, and I think that's a huge sort of area for 3D graphics. And then even smaller things like I think it should make it easy to just have, if you want to have a little animated spinning cube as a progress indicator on your website, that should be something that this should do and make it pretty easy to accomplish. So sort of that whole range of stuff. So let's take a look. I'll sort of take you through a little bit of code, hopefully sort of just try to persuade you that this is actually fairly feasible, and putting together at least relatively simple scenes shouldn't take that much effort. Should be relatively approachable, hopefully. To start, a couple design goals. Simple goals should be simple. Doing something like on the left here, just throwing a couple triangles up in the scene really should not involve a whole ton of boilerplate or a lot of complex math. And more complex scenes where you have fancy materials and reflections and different colored lights and animation. There's more going on, it's going to be a little more complex, but it should at least be approachable. It should be logical. I think there should be a clear path to get to sort of where you're going, and it should be clear what you have to do next to sort of do what you want. So let's go through, sort of start with some simple cases. Let's draw some points. If we want to just get some points in the scene, first thing we do is we create a mesh, and this is basically just pure shape, so no color or anything like that. Here I've just given a list of points, given their x, y, z coordinates, and I say mesh.points. Now I have a mesh, just sort of the shape of what I want to draw. So great. Next thing we have to do is, well, we've got some points. Where am I looking at these points from? Like what am I looking at? Where am I looking from? So we create a viewpoint. We can do that. We can just sort of say, okay, we have a focal point that I'm looking at. I have an eye point. This is where I'm looking from. And I have an up direction. That basically controls whether I'm looking like this or like this. So usually it's just straight up. Not quite done. we also have to say, I mean, so what's my field of view? So like how much angle can I see vertically within my screen? And also for some unavoidable technical reasons, we have to provide a clip depth, and this is basically how close can I actually see things. So I say clip depth of 2 feet, anything less than 2 feet from my eyes is just going to be not displayed at all. So we've got our mesh, we've got our sort of camera now, which just sort of defines where we're viewing the scene from, and now we render it. So we're going to create some HTML. We call our render function, pass a couple options. Here I'm saying that the points, I want them to be 10 pixels in diameter, pass in my camera that I created, the width and height of sort of the HTML element I want to create, and then a list of things to draw. Here I'm just drawing one thing, that set of points. So I pass in that mesh I created, and I say, please color them blue. And there's the result. We've rendered some points. That's literally all the code, other than main equals and a bunch of imports. Haven't left much out, and so it should be reasonably easy to render fairly simple stuff like this. You can sort of build on that. You can start rendering lines, very much the same. You create a mesh from a bunch of lines. You draw it blue, render it same as before. You can create triangles. Oops. Create a couple triangles. Create a couple meshes from those triangles. Now we render both of those meshes with different colors, and now we have, a little sort of scene with 2 triangles in it. Once we have, 2 drawables, we can group them together and create a sort of a composite drawable. So now we've got a square, which is just sort of a group of those 2 things we drew before. So this isn't any different. We're just rendering one thing, which is a combination of 2 other things. But now that we've got a single thing to draw, we can start manipulating that as one object. So we can do things like translation. We can take that square, and we can make a little helper function that takes it and sort of moves it up by a particular height or amount. And then I could render my scene the same as before, and maybe I just call that helper function with a bunch of different heights, and I get a bunch of different squares. So maybe this is starting to look like a building with a bunch of stories or something. I don't know. So we can sort of translate, just move stuff around. We can also rotate. We can take that square. We can sort of, define an axis to rotate around, make a helper function that rotates by a particular angle, call it a bunch of times. You get a whole bunch of rotated squares. Draw them all together, and now this is some sort of fan-like shape. I don't know, but up to you. You're probably more creative than I am. So all that's pretty cool. I think it's relatively, I think it's reasonably happy with how it worked out to create simple things like this. I think these look kind of neat, but I don't think anybody would call this realistic. This clearly does not look like something that you might see in the real world. If we want to do that, we have to talk a little bit about physically based rendering. And this is all about basically having more realistic models of what real world materials actually look like. And it's all about sort of having realistic physics-based models of how does light get created from some light source, bounce off some surface, and then end up in our eye or in some camera. And so if we want to render nice surfaces, we have to talk a little bit about how do we create lights, how do we define materials, and how do we define cameras a little more. And ultimately, if we do this right, we end up with something that looks a little bit more like a realistic blue plastic ball or something like that. So various types of lights you can create. We can create point lights. And this is just sort of a light that, like a light bulb, it exists at a particular point and it sort of spits out light in all directions. I talked about units. I really like using physical units for lighting. So for a light, you have to say that it puts out a certain amount of light, and that is in lumens. These are numbers you can just get. Like this is a photo of literally a light bulb from my closet. And the contrast is not so good. The accessibility on this container is terrible. But if you look carefully here, it says light output of 900 lumens. So you should be able to go to a hardware store, find a light, drop that number into Elm 3D Scene. We need sort of the color of the light. Color gets a little more complex when you're talking about 3D rendering. RGB doesn't really work for a variety of reasons. But one thing often you'll talk about with lights is people talk about color temperature. And so again, this light says it has a color temperature of 2700 K, 27 kelvins, and so I can just say that is a color or a chromaticity of 2700 kelvins. And then we just say, well, where is that light? Where in space is it? And that's, there we got a nice point light. You can also do directional lights for things like the sun, pretty similar. You have to give it sort of a color. Here we can cheat and just say it's the color of daylight, because that's pretty sort of fairly standardized constant. How bright is it? Sort of how much light is coming in from the sun, and sort of what direction is it coming in at. So this is noon in the tropics, so it's coming from straight above. And again, these are all numbers you can, takes a little bit more work as opposed to just specifying RGB color, but they're sort of readily available. You can look at them on Wikipedia, you can find them out of photography textbooks. You can even open up your phone with like one of the luminance meters and just get it right from there. So hopefully not too hard to sort of figure out reasonable numbers to use. And you can also do sort of ambient lighting, and this is light sort of comes from all around an object, so not from a particular direction. This sort of mimics light that's sort of like bouncing off the walls and other surfaces onto your object. So it sort of gives it, sort of bathes it in a nice sort of soft lighting, but still sort of usually comes more from above than below. So you can see this is sort of a little bit brighter on the top, a little bit darker on the bottom. Finally, materials. This is sort of the key bit that people usually talk about when you hear the word, physically based rendering. This is all about sort of realistic models of how light bounces off materials. So the two main things to think about here: color, hopefully fairly straightforward, and roughness. So a very smooth surface with a roughness sort of close to 0 is sort of very mirror-like, right? Light comes in, bounces off pretty much in the opposite direction. That leads to like very sort of sharp, bright highlights on surfaces. At the other extreme, sort of very diffuse surfaces, like something like paper is pretty close to this. Light comes in, it sort of bounces off in all directions, pretty much uniformly. And so a surface like that, you just get very soft illumination. It's brighter in the direction facing the light, but there's no highlights at all, really. And a lot of surfaces sort of somewhere in between. Light bounces off sort of mostly in the opposite direction, but there's a bit of variation. So we have everywhere from sort of very shiny surfaces, very non-shiny surfaces, somewhere in between. You can control that by roughness. And it turns out there is one more thing you need to sort of be able to specify most surfaces in a sort of fairly realistic way. And it's really complex. Get ready for this. It is it a metal or not? So this is sort of two examples, two surfaces, same roughness value, same color. One's a metal, one's not. So on the left is something, this is sort of maybe a gold ball, and this is maybe more like a rubber, plastic, yellow ball of some sort. So with those three, you can actually render a lot of surfaces pretty realistically. All right, so let's put this all together. Pretty similar to what we had before, a couple new things. We're still creating a mesh. Here I'm using sort of a helper function defined by the library to sort of just create a spherical mesh. And I say, what radius do I want and how finely do I want to subdivide that sphere. I'm creating some sunlight, like I talked about before. Give it a direction here. I'm giving it a bit of an angle, so maybe this is afternoon or something. I'm creating material. I'm giving it a color. A roughness. Roughness just goes from 0 to 1, so it's fairly easy to play around with. And I'm saying this is not a metal. And then finally, we render it. So it's sort of similar to before. We have a few more options now. Similar, we give our camera, our size. We now provide, do we have any ambient lighting? Yes. Do we have any lights? Here I just have one light, which is that sunlight I created. And I'm saying it does not cast shadows, but hold that thought. And finally, a couple more things. I have to say the maximum exposure that my scene can have. And this is basically, same as exposure on a camera. It's basically saying, how bright is the brightest white in my scene. Anything brighter than that will just be sort of overexposed. And then what white balance should I use? So if you're an outdoors scene, you have to, white balance it for sunlight. If you're indoors, maybe you white balance it for tungsten or fluorescent. And so this is, similar settings you might set on your camera, so if you're using manual mode. And here, instead of, oops, that's annoying. Instead of drawable.colored, I'm saying drawable.physical. I'm passing in that material and my mesh, same as before. And if we've done all this correctly, we end up with some sort of, I think a fairly nice looking sphere. So, I was really hoping to have some nicer demos with actually nice meshes and loading them from models and stuff. Didn't quite get to that, but should absolutely be possible, and I'm hoping to have some examples of that soon. So, a couple demos. So these are a bunch of static images, but you can absolutely animate things, right? So here's an animated scene. We've got a bunch of things. We've got a bunch of lights flying around. So say we've got a red point light. You can see it flying around and reflecting off different surfaces. We can interact with this. We can sort of turn off that red light. See what it looks like without that. Turn the green one back on. Mess around with all sorts of different things. And we can animate the positions of objects as well, move them around, rotate them, whatever we want. So that's kind of cool. Another neat bit is the way that it's set up. It's actually relatively easy to combine this with other things. So here, the colored faces are rendered using Elm 3D Scene. But all these nice dashed lines and circles and text are rendered with SVG. And it's just sort of overlaid on top of the 3D scene. And that camera object I showed you, you pass it into the scene. You can also use it to just ask, hey, this 3D point, where is that going to be on my screen? And then I can use that to draw a circle there or draw some text there, whatever the thing. So it becomes very easy to combine different technologies. And I'm really excited about these sorts of overlays. This last one, this is a combination. You may have seen some of Andre's physics demos. We saw one of them in an earlier presentation. So this one is, I've taken one of his physics demos and I've ripped out all the view code and I've changed it to render using Elm 3D Scene, added some materials, added some shadows. So hopefully this display is okay here. So notice that we've actually got sort of all those objects are casting shadows on all the other objects. With apologies to Body, this is not running quite at 60 frames per second. But I think, with a bit more optimization work, maybe a slightly smaller scene, and also maybe if we weren't running the entire physics simulation at the same time, I think we could get there. So let's show that another one because I think it's fun. So. Cool, all right. So, hopefully at least a few of you asking, all right, can I use this thing? The answer is yes, with an asterisk. It is not yet published as an Elm package. I think it's mostly complete. The API I'm pretty happy with. It's not yet fully documented, or really at all documented. But it will get there, I assure you. So for now, what you can do though, if you check out the repository, I've got a link in the next slide, you can just go into the examples folder, fire up Elm Reactor, and start playing around with it. So most of the examples I've shown here are there. You can play them yourself on your own computer. You can start messing around with the code and seeing what it looks like. And again, full release with docs should be coming hopefully pretty soon. In terms of next steps, there's fair bit of stuff there already. There's a ton of stuff I still want to add. Textures is a big one. It's almost embarrassing that's not in there right now because that's a pretty crucial part of a lot of 3D rendering. But that will go in very soon, maybe even sort of, by the time it's fully released. Kind of few other things I'd like to work on, things like transparency, so you can have like windows or glass balls and see things behind them. That adds a whole other level of complexity to the underlying engine. But hopefully at the API level, it's just a matter of giving a transparent color instead of a non-transparent color. Lots of performance optimizations that I like. Basically, getting a happier caterpillar. I'd like to do a couple of things, like I think if you have a data structure that defines a 3D scene, sure, we can render it in the browser. Why can't we also take that and export it to something you could open up in Blender or YAF-Array or any of these free ray tracers and get sort of a really nice 3D rendered version of your scene? I think some really cool opportunities there. Like to throw in a debug mode so you can see like where are the actual triangles that I've rendered and what are their normal vectors and why isn't my thing rendering properly? So I think lots of cool ideas. And tons more. There are like dozens of issues on the repository. Feel free to add your own. And as sort of a bonus, I'm really interested in geometry generation. So typically with 3D graphics engines, you would load up your assets from a file, right? You'd load up an OBJ file or something that somebody created in Blender. I'm really excited about actually generating geometry within Elm, like kind of as I mentioned at the beginning of this presentation. And that won't be part of Elm 3D Scene, but I think it'll feed into it. And it'll let us do some sort of really cool interactive apps in the browser without having to use pipelines that involve Blender or all sorts of other tools. So that's something I'm really excited about. So a few thanks. Andre Kuzmin for maintaining the Elm WebGL package. I also did lots of pair programming with him, so things like shadows. We worked together to sort of figure out how that worked, and then I incorporated it into this package. So he's been awesome, and I cannot thank him enough. All my long-suffering colleagues at my company, because I'm like constantly just talking Elm at them all the time. Elm NYC Meetup, they were nice enough to let me do a practice version of this talk remotely a little while ago, so I got some great feedback there. I think you're all benefiting. And the Elm community, like I love being a part of this community. I'm super friendly. I just love working with anyone. And yeah, it's just been an incredible pleasure. So if this is something you're interested in, please get in touch. I'm Ian Mackenzie on the Elm Slack. Tend to hang out in the WebGL and geometry channels. There's the repository. So yeah, clone it, fire up Elm Reactor, start playing around with it. I'd love to hear your thoughts. Bugs and feature requests are very much welcome. And if your Twitter is your thing, I'm Ian E. Mackenzie on Twitter. And pretty low volume, but I'll tend to post things like new releases and cool demos I've made or whatever. So yeah, that's that, and thank you.